Lesson 11 is chords, radii, and diameters. Radii is just plural for radius. In 11.1, we're going to start off with some vocab, and then we're going to get into a couple new theorems. So the vocab, some of it is review, some of it's new. The first one is circumference, which is the distance around the circle. It's like the outside edge of the circle, so this part. And then the second one is the radius. We've talked about that in previous lessons. It's a segment in a circle with one endpoint on the circle and the other endpoint on or at the center of the circle. So in this graphic, the radius is right here. It's that blue line. So you can see it like kind of starts at the center and it goes to the outside edge of the circle. This next word, it may or may not be new, but a chord is how it's pronounced, and it's a line segment with endpoints on the circle. So that's the yellow segment in the picture. So each kind of like side of the segment is on the outside edge of the circle. It doesn't necessarily have to pass through the middle. If it does pass through the middle, it has a more specific name, and that would be diameter. So diameter is a chord that passes through the center of the circle, and that's the red segment on this picture. So it has like its endpoints on the outside edge of the circle, and it passes through the center. Okay, so the first new theorem, starting right here. If a diameter or radius of a circle bisects a chord that is not a diameter, then the diameter or radius must be perpendicular to the chord. So what that means is, in this picture, I have a diameter AB, so a segment that attaches to the outside of the circle and crosses through the center, and it bisects this chord DE. Bisects means to cut into two equal parts, and you can tell that it bisects because these each have like one tick mark on each side, meaning that each of those sides is equal. So if it bisects it, which in this case it does, that means that the diameter is perpendicular to the chord. So that gives us more information about the like angles around the intersection point. So that intersection point F, like all four angles around it, they would all be 90-degree angles, since those are perpendicular to each other. Okay, the second theorem is just the reverse of that, the converse. So if a diameter or a radius of a circle is perpendicular to a chord, then it bisects it. So this would be like if you are given a diameter and you see that it crosses through a chord and it creates a 90-degree angle. Because you see that 90-degree angle, that means that they are perpendicular to each other. If they're perpendicular to each other, that means that the diameter or radius bisects that chord, which means it would cut it into two congruent parts. Okay, moving down to problem solving with these theorems. So example 1, what is the length of segment ED? Okay, so in this example, we just have a radius for this one. We don't have a full diameter, but in the radius, or like at the intersection point of the radius and the chord, we can see that there is a right angle there. So if there's a right angle there, that means that those two segments are perpendicular to each other. That means that if they're perpendicular, then the like radius bisects that chord, which means it cuts it into two congruent parts, and that means that each side is equal. So if we need to find the length of ED, first we need to find x. And to find x, we can set up an equation now because we just figured out that both of those sides are equal. So we can create an equation that just says each like expression on each side is equal to the other side. So it would be 5x plus 3 equals 8x minus 9. So now we have our equation set up. Now it's kind of like back to algebra, where we want to like get our x's together, and then we want to get x by itself isolated. So we have 5x plus 3 equals 8x minus 9. Whenever I have like x's on both sides of the equal sign, I like to get them together as like kind of my first step, or if it's possible. So I have a like 5x and an 8. I don't really like dealing with negatives if I don't have to, so I'm going to subtract the 5x to cancel that over. If I subtracted the 8x, that would end up giving me a negative. So I'm going to subtract 5x from this side to cancel it out. And then I'm also going to subtract on this side. Whatever I do to the one side of the equal sign, I like have to do to the other. So the 5x minus 5x cancels. And then I can bring down the 3. And then 8x minus 5x is 3x. You just subtract the numbers in front, and then minus 9. And my ultimate goal when I'm solving is to get x completely by itself. So now I have to start like moving things away from the x. It's 3x minus 9, and usually after this point we undo addition or subtraction first, which means I would want to cancel out that minus 9 first. So the like opposite or the inverse of subtracting 9 would be adding 9. So I'd add 9 right there, and then I'd also need to add 9 to this side to keep the equation balanced. So 3 plus 9 is 12 equals, and then I would bring down the 3x. And then negative 9 plus 9, those cancel out, or minus 9 plus 9 cancel out. And then still trying to get x by itself. So now I have a 3 times x. So to cancel out multiplying by 3, I would divide both sides by 3. So 12 divided by 3 would leave me with 4, and then 3x divided by 3 would leave me with just x. So I end up with x equals 4, and then a really easy mistake to make on a problem like this, and I make it all the time, is to like think that we're done with the problem because we solved for x, but the question is asking what is the length of ED. So we're trying to find this entire length right here. So now what we have to do is we have to take 4 and put it in for the x's to actually like find each side length and add them together to get the total length. So what that's going to look like is for the first one, it'll be 5 times 4 plus 3. And you have kind of two options. We can like get this side and then double it if we want to because they're the same length, or you can just also like add the 8 times 4 minus 9 as well. So we just kind of put 4 in for like the x's. And again, you can do like the whole thing like with both sides, or you can get one side and double it because they're the same length. So 5 times 4 is 20 plus 3 plus 8 times 4 is 32 minus 9, and then now we can add / subtract all of them. So 20 plus 3, 23 plus 32, and then minus 9. So it ends up being 46. And if you went like the find one side and double it route, you should have found that one side was 23, and then you would double it to get 46. So the length of segment ED is 46. Okay, so moving on to example 2, it says, what is the value of x? So for this one, we have like a diameter that is cutting a chord in half. That means it's bisecting it. We can tell by like the 2 tick marks on each side. So we know from like the original theorem that if it bisects it, it creates they're perpendicular. So that means that it would create a 90-degree angle. So segment VT and EF are perpendicular because you could see EF got bisected. So perpendicular means it creates like 4 right angles all the way around. Right angles are like 90 degrees. So all 4 angles around like point K are going to be 90 degrees. So if we want to find the value of x, we can take that expression that is given to us in that angle and set it equal to 90 degrees. So it'd be 5x plus 65 equals 90 degrees. And then you could see like on the angle it has like this whole thing in parentheses with the degrees to show this in degrees. I think I'm just going to take all of the degree symbols off. So 5x plus 65 equals 90. Same thing here, we're like trying to solve for x. So that means getting it by itself. So first I would cancel out that like adding 65 by subtracting 65 from both sides. And then I would bring down my 5x, and then 65 minus 65 cancels out. And then 90 minus 65 is 25. Just double checking it. Sorry, 90 minus 65 is 25. And then from there, we want to get x completely by itself. So that 5 is being multiplied by x. So to cancel it out, I would divide both sides by 5. 5 divided by 5 cancels out, and then I'm left with x equals 25 divided by 5, so 5. And then for this problem, it just asks us what is the value of x. It doesn't ask us for the angle measurement, it asks us for what x is, so we're done here. If it asks us for just the angle measurement, that would actually be faster because we know that those lines have to be perpendicular, so it would just be 90. Okay, moving down to 11.2, there's 2 more new rules or theorems for this section. This has to do with if there's 2 chords within a circle. So it's just one theorem and its converse. So the first one, if 2 chords in a circle are congruent, then the center of the circle is equidistant from the 2 chords. So I'm going to use this picture to the right as an example. If AB and ED are congruent, I'm going to actually move these. If AB and ED are congruent, that means that those 2 chords are equidistant from the circle, meaning they're the same distance. So if I were to create a segment that shows the distance from the center to the segment, these would be equal. They would have the same exact distance from that center. So that's the first one. We would be given the fact that they were congruent in that case. And then for the second one, for the converse, if the center of the circle is equidistant from the 2 chords, then the 2 chords are congruent. So this time we would be given the distance from the center to the chord. And if we're given that distance is congruent, then that means that we know that the 2 chords are congruent as well. So it's really the same theorem, it just kind of is ordered differently. And so the way it would appear differently in problems is dependent on what information you're given. So the first one is you're given that the chords are congruent. The second one is that you're given that the chords are equidistant from the center. Okay, so example 1, how long are the chords? So in this one, we are given the 2 chords, we have expressions for them, and then we have these segments that are kind of in the middle that are showing the distance from the center to the chords, and they both have that 1 tick mark. So that means that they're the same distance, so the chords are equidistant from the center. And if the chords are equidistant from the center, then they are congruent as well. So that means that AB would be congruent to ED. So if they're congruent, we can take those 2 expressions and set them equal because they're both the same length to be able to solve for x and eventually be able to find the length of the chord. So we'll take 2/4 x plus 8 and set it equal to 9/2 x minus 24 because each of those segments is the same length, so their expression should be equal. So 2/4 x plus 8 equals 9/2 x minus 24. It's driving me crazy that 2/4 is 2/4 in this problem and not 1/2. So I'm just going to go ahead and reduce. So how if these both have a common factor of 2, I can reduce them. So that's what I'm going to do. I'm just going to go ahead and erase the 2/4 and put a 1/2 there instead. And then there's kind of 2 options as far as solving this problem. One of them is by clearing the denominator if you don't want to deal with fractions. In this case, it's not that bad to leave it as is just because our fractions have the same denominator, but you can always multiply the least common denominator throughout the equation to cancel it out if you wanted to. So for this one, I want to get my x's on the same side of the equation. So I'm going to take this 1/2 x and subtract it over to the other side. So I'll do minus 1/2 x and then minus 1/2 x right here underneath the 9/2 x since those are the like terms. 1/2 x minus 1/2 x cancels out. I bring down the 8 and then 9/2 x minus 1/2 x. When you subtract fractions, you only subtract the numerator. So you would do 9 minus 1, which is 8/2 x. So just subtract the numerator, the denominator stays the same. 9 minus 1 is 8, denominator is still 2. And then I would bring down this minus 24. And then now I have 8 over 2, which that just means like 8 divided by 2, so it's 4. So we might as well change it to a 4x just to make life easier. So 8 equals 4x minus 24. And then my ultimate goal now is to get x completely by itself. So I want to cancel out that minus 24 by adding 24 to both sides. 8 plus 24 is 32. Bring down the 4x. And then minus 24 plus 24 cancels out. Still trying to get x by itself. There's a 4 that's being multiplied by x, so I'm going to divide both sides by 4. 32 divided by 4 is 8, equals 4 divided by 4 is just 1, so this becomes just a 1x or just x. So we end up with x equals 8, but kind of same thing as the very first problem where we're not asked what we're not asked what x is, we're asked what the length of the chords are. So now if we want to figure out the length of the chord, we have to take that like 8 equals x and put it in for x in either of the chords. This time we don't have to like add them together or double it. They're just like the same length, but they're not like kind of one continuous segment or anything like that. So we really just need to pick one of them that we want to use. I'm thinking AB would be the best one, and put 8 in for the x there. So it would be 2/4 times 8. It's kind of messy, sorry. 2/4 times 8 and then plus 8. So we're taking like this expression right here and putting the 8 in for x. You can use either one though. You can use the 2/4 or the 9/2 minus 24. 2/4, remember, is the same thing as 1/2, so I'm just going to change out for 1/2 because it makes everybody's life easier. And then if we multiply these two together now, 1/2 times 8 is the same thing as half of 8, so half of 8 is 4, and then plus 8 is 12. So we end up with 12, and that's the distance of like AB, but we just kind of talked about how like they're the same exact length, AB and ED, so that's going to be the like length of each of them. So we can say like AB is 12 and ED is also 12. And I'm just going to zoom out really quick and talk about why like we didn't need to add these two together. So like when we did that up here, it was because we found like this side and we had to add them together to get the entire like length of the chord. Down here, they're just two completely separate chords that just happen to have the same length, but they're not connected, so we wouldn't need to add them together. Okay, so this is the last example. So given that segment AG is congruent to BH, so I'm going to start filling this in. AG is congruent to BH, and DO is x minus 9, so that's, let's see, this little guy in here, DO is x minus 9. And then EO is 4x minus 90. So EO is 4x minus 90. Sorry, it's kind of hard to fit it in there. What is the length of DE? So we're trying to find like this entire length right here between those two kind of like green highlighted lines. So to understand this one, we're going to need that first theorem from this section. So up here, if two chords in a circle are congruent, then the center of the circle is equidistant from the two chords. So in this case, the two chords are those green highlighted segments, AG and BH, and we're told that those are congruent. So each of those kind of equal each other. They have the same length. So if they have the same length, that means that they are equidistant from the center. So that means that those little segments that we were looking at that are like the distance of those chords from the center, those must be equal or congruent. So like DO is going to be the same length as OE. They're congruent to each other. So if we want to find the length of DE, we first need to find X. And then we'll be able to like take that x to be able to find the full length. So if those two like kind of mini segments, DO and OE, are equal or they're congruent, I can take their expressions and set them equal to each other. So we can set x minus 9 equal to 4x minus 90. So x minus 9 equals 4x minus 90. I have another problem where I have like x's on each side of the equal sign, so my first priority is going to be to get them together. This is a 1x, so I'm going to subtract that one over. So I'll do minus 1x under the 4x because those are like terms. 1x minus 1x cancels out. I'm going to bring down the negative 9. 4x minus 1x is 3x. We just subtract the coefficients, and then I'll bring down the minus 90. And then now I have just like an x on one side, so I'm going to try to move everything away from it. So that minus 90, I'm going to cancel that out by adding 90 to both sides. So negative 9 plus 90, that would be 81, equals 3x. Still trying to get x by itself, and now I just have a 3 that's being multiplied by it, so I would cancel it out by dividing both sides by 3. 81 divided by 3 is 27. Equal to x. So we found the length, or like the value of x, but again, this problem is asking for what is the length of DE. So a couple of different ways that we can find it. We can take both sides and add them together, so it'd be like x minus 9 plus 4x minus 90, and put the like 27 in for both x's, like right here, and just add the whole thing together. But since we know that like each of those segments is congruent, we can also just find one side and then double it. And I think for this problem, it makes a lot more sense to do that because I don't really want to deal with the 4x minus 90. I would much rather just take 27 for x and put it into this x and just double that number. So if I find one side and I double it, then it'll give me like the total distance, like DE, the full segment. Okay, so that's what I'm gonna do. So we'll take this x minus 9, but I'm gonna put 27 in for x instead, and then subtract 9. So 27 minus 9 is 18. So 18 is the length of one segment, and then now I would just need to double it. So times 2 would give us the like full length. 18 times 2 is 36. So the length of segment DE would be 36. And it really is just like personal preference. If you'd rather just like use the full thing, like x minus 9 plus 4x minus 90, you would also get to 36 as well. I just thought this one, I didn't really want to deal with the 4x minus 90, so it makes it easier just to like kind of take one side and double it.